Okay, students, let us begin the class. In this week's, we want to explore on effect of extra pole and extra zero. Yeah, and then after that, we will design a controller to reject the disturbance. We repeat again the same thing, but we want to see another approach, yeah, on rejecting the disturbance. Wait. So I want to remind you again about the project. Yeah, the ball bearing is available in IoT Lab, so you can readily construct the joint. Okay, the due date for step 1 is next week, remember? Yeah, and the whole project accounts for how many percent? 25%. Yeah, almost the same like your exam 1. Yeah, so and then I will rank your participation, yeah, in doing the project. So if you don't do anything, then your score will be low. But if you are actively creating the model, then you get high score on the step 1. Okay. Any question on this? Next week the due date, yeah. You only have 1 more week. Don't do it 1 day before the due date. For sure cannot finish. And then if you say, sir, can you open IoT Lab until 9 p.m.? No, cannot. Okay, don't force yourself. No, don't force me. Okay. Can you simulate this on Simulink now?
Yes.
Yeah. So you just drag the transfer function. You will have 2 transfer functions. So this will be the result of your transfer function. I created 2 models here. The top one is the original one. The bottom part is the one that we want to modify. Okay. They are the same one, but we want to adjust the first order system in here. Okay, we want to adjust the pole for the first order system. So you will have your second order poles in here, yeah, and then we want to try to vary the 1/tau, yeah. So in here it's 1/tau. This is 1/tau, yeah. So you know that this zeta omega n, okay. You set zeta to be 0.2, omega n you can do, let's see how I check it. I think I have, yeah, my omega n in here is 10, and zeta is 0.2. My omega n is 10. So the zeta omega n in here is -2. Okay. So I have -2 over here. Yeah. You don't have to follow the script. If you are confused, you just follow this. Okay. If I double click, just write down this. Okay. So the entries of denominator, you just write down the variable, and then you define the variable on the callbacks. Yeah.
Oh.
What?
Max.
This one?
Yep.
Mux. MUX.
Yeah, Max.
Okay, on this, yeah. So you have second order system and then first order system over there. If we set tau to be 0.05, then this will be minus 20, yeah. See? Okay, minus 20, yeah. So from minus 2 to minus 20, that's 10 times. You can also define your second order system like this. Okay, the Simulink.
This one you define all of it by yourself.
Yeah.
Oh my God.
That one is in the border form, this one is in advanced form, but they are the same.
What is the powers?
What? 2 zeta over omega n.
2 times zeta.
2 times zeta. Yeah, I'm using the border form because I want my output to be 1 and I don't want to bother with adjusting the constant over here. Okay, so that the final value is 1. Yeah, in this format, the final value is 1 over omega n squared.
Oh.
Which one? This one again? Just now I showed it to you, right?
Me too. What is the difference between
Between what? Star. Star.
Oh, after the power of 2 there's space.
There is a space. You have a space here. Space and then space.
Okay. How to define the omega n?
You define the omega n, you go to model properties. Here, yeah, you have the model properties.
Model properties.
And then there is callbacks here.
I have no file.
And then init function. The init function. Which is why just don't bother with that. You have the omega n, you have the zeta, right? So you just compute all of them. Just compute all of them 1 over omega n squared. So you just put your 1 over omega n squared, s squared, in here is 2 zeta, and then plus 1. Okay, so this will be your transfer function. You still confused?
Hitung bro, 1 per omega n square-nya.
You have zeta omega n, right? Just compute this.
Hitung.
What is omega n squared?
100.
100. Okay,
Oh, yeah.
so 1 over 100.
0.01.
So you have the 0.01 s squared plus 2 zeta over omega n. What is
the second one?
the same? Say it again, I don't understand.
For the substitute only for the second.
The second row, this one? Denominator. The first row is 1.
There's 2 rows, right?
This one and this one, they are the same. They are the same. We want to change only the first order system. Okay.
So we substitute all Wn with the
Yes, with this. Okay.
Gimana lu bisa better? Like it. Oh my God. This one, the black one.
What moves?
This is 0.01, this is 0.04, and this is 1. Okay, done.
Cancel. Dah.
Okay, done. Anyone confused? Anyone still confused?
Ini
Okay. I'll just replace this lah. This is so confusing to you.
0,01, 0,04.
Kayak gitu kalau kamu define variable.
Kalau dia udah di define bisa. Nah, sekarang kan kita belum mau define.
Oh, kita masukin itu.
Masukin omega n, masukin zeta.
Okay, now I put all of the numbers there. Okay lah, I cannot take it anymore.
Kita juga.
Okay, I'll give you 1 point if you get it done correctly. Okay. 1 point. 0 point here. Okay. 2 times 0.04. 5. What is it? 0.05. Let's start. 0 point. 0. This one.
No S, no plus.
Mana?
No plus.
No plus.
Masih.
Ya.
Yeah, they're still the same. We are still using the same first order system.
Nah, Pak, itu ada pangkat, ada pangkat.
Jadi gimana?
What is it?
Udah denominator nomornya tuh.
Pangkatnya?
Coba.
Okay.
Nomornya.
Plus 1. 0.
Mana?
Still 0. Huh?
Udah. Besar.
I don't care. Still 0. No, not yet. This one?
Tunggu.
More.
Udah stop.
Enggak ada.
Okay, let's move on.
Bro, delete that one. Is the transfer function? This is transfer function.
So you see, now you label the signal. Can you do it? You double click and then you write down the signal. Yeah, you double click on it. Double click on the arrow and then you write down the signal name. Yeah, and then after that you double click on the scope. You go into settings on the scope. You check on legends. Check legends, yeah, on the scope. Understand this? Do you follow? Do you get it? You set legend. Okay, legend is on. Yeah.
Reload, bro. Pakai jangan yang online.
Nggak punya.
So once you do that, I want you to adjust the tau on the bottom system. On the system here on the bottom, you adjust the tau. Yeah. You increase the tau so that the number the first order system pulse moves to the right side. Okay. You understand? Yeah. So we want to simulate the two systems. The first system has 1/tau to be 20. The second system, we want to move the 1/tau to the right side. Yeah, and see what's the effect. Okay. You change it up to you, but just that it is almost close to the zeta omega n. Yeah. Yeah, between -20 and -2 lah. Okay, 1/tau is between -20 and -2. So you can adjust the tau from 0.05 up to 0.5. Yeah, you adjust between the numbers. Okay. What do you observe?
The response difference.
Yeah, different. How different it is?
If no overshoot, sir.
What happened with the overshoot?
Decrease. Decrease kan? Wait, yang biru tuh yang mana sih?
Oh ya, sebelum increase.
Hah?
Aku salah baca lagi.
Okay, yeah, the modified system has less overshoot. Okay, so this is what we discussed last week. Yeah, about the overshoot. When we have an extra pole to your system, it can make the overshoot to be smaller. However, as you can see, the response is slower. Yeah, it is slower. If you keep increasing the tau, what will happen?
But that's the range. Pas bro, kita full number bro.
Okay, it becomes even more slower. Okay, so that's the effect of extra pole. Any question on this?
Why is it extra pole, sir? Isn't we only change the tau?
Yeah, tau makes you have an extra pole. This is extra pole, right?
Yeah, when you time.
Okay, you have a second order system in here, and then you add another first order system in here. That means you have extra pole.
Oh, that's what it means.
How come you don't understand? This is a simple block diagram. Yeah?
So if like this, can we consider third order?
Yes. Yes. This is a third order system. Any question on this? What if I move the first order system to the left side?
Same lah.
Are they the same?
Yeah, same. Proof.
Some students are not confident.
Same.
Black shirt. Are you sure?
Sure. First multiplication. That's right.
Yeah. But just now some person said, huh, what extra pole? Now you said yes, confident. Okay lah. All right. Let's move on to the next topic. This exercise we have it last week. Yeah, last week I computed this for you. Yeah, we have zeta to be 0.2, and then omega d 2.9394, and so percentage of overshoot analytically is 52%. Yeah, after we add the third pole in here, which is -2, we have to use the if you want to predict, yeah, using the graph, then you use figure 7.3. It is available in the module or also in the lecture notes that I shared to you. Yeah, you use this graph, but first you have to compute what is the beta. Yeah, beta is 1 over tau divided by zeta omega n. Okay, that is beta, which is given in here. Okay, so you just read from the graph. There are several plots here. Each plot is for a certain zeta. Yeah, you have zeta 0.2, 0.3, 0.4, and etc. And then based on the data, we have overshoot of 20%. So overshoot reduced when we make the extra pole close enough to the dominant pole. You get less overshoot. Analytically, we have this, and then by simulation, you see in the Simulink. Yeah, so don't make mistake in the exam. Question?
So what's the comparison for the 3.33, the less than 10? What is the comparison for?
If your beta is less than 10, then you have to use this chart.
So So it's legal to use this if less than 10.
Yes, yes.
If more than 10,
If it is more than 10, then you can approximate using the standard second order system because the pole is fast enough so that you can ignore it. Okay, the extra pole is fast enough, you can ignore it. Okay, now the next topic is extra zero. Okay, just now we have extra pole, but now in this case we have extra zero. Okay. The analysis here shows two systems. Yeah, the first system is just a second order system without any zero. Yeah, you see, is there any zero here?
Oh,
No, yeah. But the second system, it has zero. Yeah, the zero is what's the zero here?
tau.
Minus 1 over tau, not minus 1 plus tau. Yeah, the zero in here is minus 1 over tau. And then the first analysis that we do is that we want to compute what is the response if the system G2 is being subjected to step input. Okay. Now here is the situation, same kind of situation, but this is an extra pole, but in there it is extra zero. Okay, which is why it is denoted as circle. Zero is denoted as circle, pole is X. Yeah. So 1 over tau is this much. So this will be the response of your system. Yeah. Because any question?
Is the new zero 1 over tau only or 1 over tau over W?
No, just 1 over tau.
So the W unit square.
Ah, this one?
Yeah, it's times, right?
Times, but there's nothing, right? It is a constant.
Oh,
Okay, still don't understand zero, yeah? Yeah, but that's okay. But the zero is not affected by the constant. Okay. For example, if we have a system S plus 10, yeah. What's the zero here? Negative 10. If I multiply with 1000, what's the zero? Still minus 10, right? It's not affected by this one. Okay. Okay, let's move on. If we want to find out the response of the system G2S, because the top part consists of two parts, yeah? The first one is a constant 1, the second one is tau S. So we divide two kind of system. This is the first one, and the second one is tau times that one. Yeah. Is this okay? Yeah. So G2 is basically you have G1, but then you plus G1 times tau times S. Okay? Okay, can you see it? Or no?
Yes.
Who cannot see it? Yeah, see. Okay. So you see, this is G1, yeah? G1 is omega n squared and all of this. But however, G2 is omega n squared times 1, yeah? Plus this. So this one is G1 itself, right? Yeah. So the omega n squared times 1, everything is the G1. Okay. Okay. And then the next term is just you have the tau S multiplied by G1. So we have this term. Okay. Is this okay? Move on, yeah. And then the next step, we express the output CS with input to be the step function. And then by using partial fraction, not partial fraction, actually, you can just find out the response using Laplace table, yeah. And this is the response. So you notice that this is the original response of the system, okay, and this is the extra term because of the extra zero. Yeah, this is the original one and this is the additional term. Yeah, So we have the same thing analogous to beta. We call it gamma now. Yeah. If gamma is less than 10, then you have to use figure 7.6 to see the overshoot. If the zero is far away from the dominant poles, far away to the left, I mean, yeah, then it will not affect the overshoot. Yeah. See, the same kind of computation that you do, then you use the figure to estimate what's the overshoot. Okay. Any question on this?
Confused how to use the figure.
You use the figure. Okay. Now you compute first your zeta. Your zeta on your second order system, the original second order system, compute the zeta first. And then you choose this curve which corresponds to your zeta. And then after that, you compute your gamma, right? The gamma is the horizontal axis in here. So let's say if your gamma is 1, 2, 3, your gamma is 3. Your gamma 3, then you use this line. Okay. If let's say your zeta is 0.4 and then your gamma is 2, then you use this. Yeah. Then you pull it to the left, that will be your overshoot. Yeah, in percentage. Gamma. Yeah. For extra zero, it is gamma. Yeah.
Why is it gamma less than 5/10?
No, this is typo. Yeah, less than 10. Yeah. No, the original one. Original one. No, the zeta is your original zeta, the second order zeta. Okay.
So gamma is a new variable when we have extra zero.
Yeah. It is a new variable to help you to compute the overshoot.
The typical question would be like, how many percentage does the overshoot reduce?
Yes.
I think this
Yeah. Any more question on this?
Oh,
Yeah. For a third order for second order system, that's correct. Second order system which has extra zero. For example, if you have s plus 3 and then this is s squared plus 2s plus, let's say, 1.5. Okay, then this applies. Okay, second order system, but then you have zero on the top. Okay, then you can use. Okay, now you simulate the system with Simulink.
This times the now one.
Nah,
This is the modified.
no, this is already your system.
Okay.
Yeah. So you have only one system, this one. And then what I wanted to do is that you adjust the zero on the top. Adjust the zero, make it closer to the dominant pole. See what happens. Sorry? No need. So what you will do in here is that we can ignore the top one. Top one no need. Okay. And then we can remove this one also. And then I can write down 140. Then what else do we have? Yeah, 16.49. Right. So if I simulate, I will just see this plot. So that's the plot, yeah. So in this case, the zeta is very big, yeah, 0.8, pretty big, 0.8, which is why we don't see a lot of overshoot in here. Sorry. Okay, and then something is not right. And then you change your pole, your zero, yeah. Let's say you reduce by half to -20. See what happens.
Same.
Okay. How about you change to 10? If it is 10, what happened? Why is it PI? Oh. Okay, let us change again to 5.
Oh, different.
Ah?
4 and yeah.
Is it different? I cannot see clearly from here. They seem to look the same, yeah.
Difference.
Yeah. Oh, wait. It's just the
This right?
4 and 4.
4 and 5. The 14 masih.
okay. Yeah, there is a difference. Okay, so you see there is a change right now. So when you keep moving your extra zero closer to the origin, you can see a big overshoot. Okay, so if extra zero, if you're not careful, it can make your system to be more oscillatory. If I set my zero to be on the right half plane, will my system be stable or not?
Zero, kan?
Zero.
If my zero is on the right half plane, will it still be stable? Stable, yeah. Let me move it to the right half plane. -1, and see what's the result. Yeah, you see, it is still stable. If you make your pole to be on the right half plane, that's not stable. This is still stable, but the response is very different.
What is it, Mister?
Yeah, that means your final value is here, yeah. But then your system wants to go up in the beginning, but then finally your system has to go down. This is called the non-minimum phase system. Non-minimum phase system behavior is like this. The first, you go to the left, and then after that you go to the right side. So it happens when your zero is on the right half plane. It's not good, okay? It is stable, but not good. Sobri. Coba sini. Come here. An example of this is that, let's say you want to run. Normally, if I ask you to run to Nathan, what do you do? Run now. Okay. Yeah. Now, if it is non-minimum phase system like this, if I said run, you go back first, and then you go.
Mobil-mobilan yang ditarik itu.
Yeah, it's like this. Okay. Okay, thank you. Have you seen that kind of situation? Yeah. In Sundanese, it's called ngawahan. Ya. Ngawahan. Nah. So at all costs, if you can avoid to have a zero on the right side, right half plane, yeah. Okay. So just now it was a very extreme case because the original system has zeta of 0.8, yeah, very large damping ratio. But then because we move the extra zero close to the origin, the system oscillates. It has overshoot. Okay, extreme case. Okay, the next thing about zero. Yeah, this is still about zero. I want to say here with this fact, it will be used later when we discuss the Nyquist stability criterion. Okay, but I want to tell you now that your system, the closed loop system, yeah, you have the feedback path over here and then the forward path over there. Each of the block has zero and pole on their own, right? Yeah, usually, yeah. So you have your zero over here on the feed forward path. You have your zero here on the feedback path. This is the pole and that's the pole, okay? And then when we create the closed loop system, this is what we have. Can you see what is the zero here? Zero is A and the D, yeah? So A and D, which is the zero of the closed loop system, they are the zero of the open loop one and also the pole of the feedback path. Okay, so that is actually what happened. What does it mean? I said to you just now, yeah. Just now I said to you that when you design a system, you try to avoid having your zero to be on the right half plane. Okay, so that means you have to avoid having DS to have a zero on the right half plane, also DS to be on the right half plane. You want to avoid that. Yeah. If you can do that, then your system is okay, it's safe. Any question?
So in other words, all of it has to be left.
Yes.
In other words, everything has to be left.
Yeah.
For the system to be in good shape lah. Yeah, one thing that you cannot change is that if let's say your plant have a zero on the right hand side, if your plant itself has zero on the right hand side, then the A over here, it has the root on the right hand side. You cannot avoid that. Yeah, clear, yeah? Then as a result, this will happen on the right hand side. So normally a system that behaves like that, it is because of its inherent model. Because the model is like that. Yeah, we cannot change the model. Yeah, now I want to discuss about stability with you. Do you remember the? I think I just exposed the system now because we will discuss this system, yeah, on the disturbance rejection. Yeah, you still remember this?
Yes, yes.
Yeah, okay. Now I want to test your understanding. 1 over ms plus c. Is this system stable?
Yes.
Stable, yeah. So we said last time that if we want to get from this original transfer function to the velocity, we multiply by s, yeah, correct?
That's right. Terus bikin integral ya. Yang belum kan? Oh,
Ya, ya, tidak.
ya, direct.
Kan Z.
So if you want to get it from the velocity to the displacement again, what do we do?
S.
Huh?
S.
We multiply by 1 over s.
Balik.
So this is a stable system, okay? And then once we have up to the displacement, it becomes, is it stable or unstable?
No.
From here to here, is this stable?
Yes. Mostly stable.
Oh, what?
Yeah. S is S0.
Yeah, so it is not Bibo stable, yeah.
Oh yeah.
What's the word? Literally.
Yeah, it is neutrally stable, okay.
Oh yeah, kan S equals to 0 ya.
Yeah. So you see, actually, when the original system is like this is your input and this is the output. This is unstable system, yeah, unstable. But when you cut inside like this, from here to here, it becomes stable. Okay, so from a system point of view, this is weird actually. Okay, you have a stable system inside an unstable system. Okay, so that is weird, because from a system's point of view, when a system is unstable, then it is just unstable wherever you see it. Yeah, when we have this differential equation over here, how many physical variable that we observe? Yeah, how many physical variable that we observe? Actually, there are 2 only, yeah, that we observe. The first one is the velocity, and the second one is the displacement. Okay, the displacement and the velocity. So based on that analysis, the velocity is stable, however the displacement is not. Do you understand that? Okay. So the whole system, if we only select a certain output from it, we can see that the system is stable, which is why we call it bounded input, bounded output, because we only see the relationship between input and output. Okay, not the whole system's behavior. The whole system behavior, it is unstable, yeah, from here unstable. But when you cut inside like this, you find it is stable. Yeah, so I wanted to see when you are viewing a country, let's say a country, how many variables that you see when you see a report of a country. You see the number of unemployed people, let's say. You see what's the gross domestic product. Yeah, when you are seeing only good things, then you are actually only you are seeing only this stable part. But actually the whole system inside, it's unstable. Okay, so that's what actually happen every day. Yeah, when I see you, Anthony, what you what you want people to see from you is your stable form, right? Anything inside you, I don't know what happened. Who knows if it is jumping all around. Yeah, chaos inside. Yeah. uh, so the transfer function method that we see right now, yeah, we cannot see the whole thing. Yeah, we only select a few output to be analyzed. Okay. However, when we discuss the system later in state space, we can see the behavior of the system in a whole. Yeah, if it is unstable, then it is unstable. Okay, no matter what kind of output that you want to observe, if the system is unstable, then it is unstable. Okay, so just be careful when you are working on transfer function. Yeah, let's move on. Yeah, last time we discussed when we are using the proportional controller, we cannot eliminate the disturbance completely. Yeah, this FW divided by KP, if we want to make it small, then we need high KP. When we use the proportional and integral, I think last time we also derive it. Yeah, here. Yeah, still remember?
It's a homework.
It's an homework. Yeah. So when we have the S on the top here, yeah, this S eliminates the disturbance. Yeah, the Ki terms that we have, Ki over S, makes the S to come out for the FW. Okay, and so based on that, the steady state value is equal to the desired velocity. So we eliminate the disturbance. What if we use the PID? This is the case when we use PID. Yeah, the same result. But what I want to discuss is, what about the closed loop poles of the proportional and integral? When we discuss the closed loop poles, which part that we see from this? Which part? Yeah, only the denominator. Yeah.
It's the same.
Yeah, they are the same. If they are different, then you are making a mistake in deriving it. They cannot be different. They have to be the same. Only numerator different. Yeah. So based on this, what will be the zeta omega n square from this?
Yeah, square is square root of Ki
Over m. Yeah.
over M. Yeah.
And that's the zeta will be this one. Yeah. And the zeta omega n is this. So my question here, what happened if we increase Kp?
KP.
Yeah, if we increase Kp, what happened with the closed loop poles?
Zeta smaller. Zeta increase.
Zeta increases, and then
Zeta
What?
omega n increase.
so you mean we can move this one to more to the left?
The right.
More to the left, I mean.
Yeah.
Left.
Karena kan
Oh yeah.
Yeah, more to the left, yeah? Okay. Is there any limit? Let's say you cannot obtain faster pole no matter how much we increase Kp. What do you think?
Kp is limited until zeta equal to 1.
Zeta equal to 1.
No. It is limited by the torque.
Now let's say torque is unlimited.
Okay.
Yeah. I mean limit in increasing Kp in terms of the closed loop pole. What do you think?
Ya. Itu kan ini harus S kuadrat sama S2 zeta.
You increase Kp, yeah, this part will become bigger, and also zeta. What happened with zeta? Zeta will become bigger also, yeah.
W ya?
So if zeta becomes bigger and bigger, will the response also faster?
Oh, slow.
No, zeta big, is the response fast or slow? Big zeta, yeah. Zeta is damping.
Yeah, small
But,
zeta means less.
Big zeta means more damping, right?
Yeah,
More damping,
Oh,
so
yeah.
more slow.
More slow.
It will be slow. Okay, it will be slow. However, zeta omega n in here, we also make it bigger. So there is some kind of contradiction. So what actually happened? Yeah, yes. What do you think? What is the fastest pole?
Closest to zero.
Fastest ball berarti yang paling dominan.
No, not the most dominant, but the leftmost pole. The leftmost pole.
The closer to zero.
No, the leftmost balls mean the less.
Increase Ki.
What happened? You increase Ki? Increase Ki, omega n increases. No. Okay, while I'm writing here, I want you to see what is this omega n square that I draw here. What is it? Hypotenuse. Yeah, correct. It's hypotenuse. Okay. So actually, if you make a circle using omega n square as the radius, that's where the position of your closed loop poles when it is under dam. Omega n square will be the radius of the pole's location if it is under dam. Okay. So when it is under dam, you cannot increase your omega n. Yeah, unless you change your Ki. Okay. So we have our system Kp plus Ki, Kps, and this 1 over ms square, ms plus c, yeah. Okay, so we have open loop 0 there, open loop 0, which I will draw here. The open loop 0 is minus Ki over Kp. Okay, this is minus Ki over Kp, and then we have open loop pole, which is 0 and minus
0 and minus T over M.
minus
T over
C.
M.
Okay, that will be our 0. So another situation is that if we have, of course, we can change the value of Ki and Kp so that the 0 is on the left side of this pole, yeah. Okay, we can do that, right? What we cannot change is our minus C over M, yeah. It stays there. That's 0. And then we have our minus Kp, Ki or Kp. Okay. So what I'm going to discuss here is a root locus. This is a preview of our discussion later. A root locus. What will happen in here is that if we make our minus kp over k over kp over here, then the roots or the closed loop poles, it will stay here. That will be for closed loop poles. It will just stay there and stay there. No. In the real axis. They will stay in the real axis. Okay. So you can keep increasing your overall gain in here. Keep increasing overall gain, but the fastest dominant pole that you can get is just minus ki over kp. The other pole will go all the way to the left, to the minus infinity. But the other one, the dominant one, will stay here. Yeah, this is the case when the system is overdamped. Yeah, that's overdamped. Meanwhile, for the case that underdamped, situation is like this. Okay, there will be poles over here. I mean closed loop poles, and then it will go like this. After that, goes here. Okay. So the closed loop poles, yeah, as you increase, okay, I will put a constant k over there. Okay, a constant k which multiply with this. When you increase your k, the closed loop pole will go like this, and then one go up. You increase the k, yeah, goes like this, and then meet here, and then one go to the right, one go to the left. Okay. So the same thing with this. The biggest, the fastest dominant pole is still minus ki over kp. The other one will go all the way to the left. Yeah. In between this, then you have your underdamped system over here. This will be your underdamped system. This one?
Yeah.
Yeah, it is a circle.
Center of it is here.
No. Now the center of it, it depends on the, yeah, on where is your open loop poles and open loop zero. Yeah, but
The fastest pole is here.
yeah, the fastest pole, fastest dominant pole, yeah.
Dominant. Yang
Dominant. Yang paling dekat nol kan?
ya.
Yeah.
Oh,
Yeah. This is here. What is it?
you say fastest pole is negative k over here.
Fastest
Yeah.
dominant.
Oh, that's zero.
No. What I mean is that as you increase your k in here, yeah, because you can adjust your gain, it will approach this. It will approach.
The fastest pole is at the value of minus ki over kp.
Or rather, another case is that if you want to make it here, that is faster than this, of course. But don't make the k to be greater than that, because if this is just an example, yeah. Let's say you set your k here to be 100. In here, your k could be 150 over here. So as you increase your k, it will go to the right side. It's not advantageous for you. It is stable. No. It is stable. Should I upload this to YouTube?
So like if p like one, really like stay at
The left go.
K 200. No, one of them will be here, yeah, and one of them will be here, because you have two poles, yeah, two poles, one over here, one over there. So one of the pole will be slower. So So for this case, the fastest is here. Yeah, sorry, not minus K over Kp, but in here when it is critically damped. When it is critical damp. Yep.
So if the K keeps going up, if the max is gonna reach the K already.
Yeah. Cannot go more to the right. Cannot.
What does pole look like? It's like a dot.
The pole is all the dots here. That's the pole. So let's say you choose a particular K. You choose particular K. Let's say what's your favorite number? 2. Okay. Let's say your 2. 2. If K equal to 2, one of them will be here. One of them will be there. 2 poles. That's it. That's your pole. This is K equal to 2. This is K equal to 2.
Oh.
Okay. So my drawing here is that the collection of all closed loop poles, if I vary the K in here from 0 to infinity. Okay. Because we can adjust the K in here from 0 to infinity, then I will get all of these lines. K equal to 100, then one of them in here, one of them in there. Double pole. Yeah, like this. Stay there. If you choose, let's say K to be 50, probably they will be there. Yeah, let's say over here.
The line is every possible value.
Yeah.
Every possible pole.
Location when we change the the value of K.
Which effect is it? Which is 0?
No, it will not affect the 0.
No, I mean, it is part of the 0, right?
No. It's not the part of the 0. You back again to that question. Open loop 0 remains the same. Open loop 0 is still here. Yeah, this one changed the closed loop poles. Okay.
Yeah. Okay, man.
Okay.
Yes.
Yeah, of course.
Yeah.
Which part? Yep. Yeah, the left one, if we assume the 0 to be in between the open loop pole, yeah, because we can adjust minus K over Kp. Yeah, so if it is there, then the system will always be over them. Cannot critically damp, cannot under them, cannot. You understand what I mean? What is minus C over M, by the way? Yeah, what is the value of C? Do you remember? C is friction coefficient, yeah? It's very small, right?
Yeah.
And then M, is it big or small? Big. So this number is small, right? Yeah, when you place minus K over Kp to be in between 0 and minus C over M, then this value will be very, very small. Small. Okay. It's almost impossible for you to make it like this. Your system will be very, very slow if you make it this situation, yeah? Yeah. The most probable situation is this. Yeah. Okay. So how to obtain that?
Example questions.
You go into your MATLAB, go to the command window. I will teach you how to do that. Let's say you define your system to have 1, 0, and 1 pole. Yeah. Let's say S plus 3 divided by S plus 5. So how to do that? Let me clear all first. Clear all. I set my numerator to be 1 and 3, and then the denominator to be 1 and 5. Okay, and then I say my G is TF num, den. Okay, that's my G. And then if I want to draw my root locus, that's the root locus. I say R locus of G. BZ, it's BZ, and then this is the root locus. Okay. So the circle here correspond to -3, and this is -5. Oh, no, not diameter. No, this is just a line. There is no circle at all. Yeah, only one pole, 1, 0. Yeah, and then if you click on the data cursor here, you see. Yep. Allah. Yeah. You can check the gain. Yeah, that's the gain. Gain is the K. So actually, your system, open loop system, is like this. Yeah, that's the open loop system. And this is when you make it closed loop. What is the closed loop transfer function from here? K S plus 3 S plus 5 plus Ks plus 3. So it becomes S plus 5. So you have K, and this is like this, yeah. And then plus 8, is it?
Yes.
Yeah. 3K?
5 plus
5 plus 3K. Why didn't you say it sooner, huh? Okay, this is 5 plus 3K. So what is the pole then?
0.
8 will be, it is -5 minus 3K. K plus 1. So K plus 1. Okay. Wait. Something is not right. One plus K. Yeah, this is correct. Okay, when K is equal to 0, let's say K is 0, yeah. If K can be 0, what will be the S here?
5.
Minus 5. Minus 5. So when your K is very, very small, your pole will be close to here.
Gain infinity.
Yeah, you see, over there is gain 0. Yeah, you see, yeah, gain over here is smaller than the gain over here. Yeah, as you increase your gain, it will move here. So in fact, when you increase your gain, your system will become slower. Interesting, yeah. You increase your gain, but your system becomes slower. Yeah, stupid controller designer. But that's the situation. Yeah, the situation like this. We have -3, and this is -5. Open loop pole, open loop 0. Yeah, the closed loop pole will depart from open loop poles, and it will end at the open loop 0. So it will move from here to here. Okay, now you know how to modify, to find out the root locus, okay, for any kind of transfer function that you have. Okay. Yeah, for a homework on Wednesday's homework, I wanted to think about the closed loop poles for the PID. Okay, I give you this already, but then I want to ask you what's the role of the derivative constant in there. Yeah, from the PI controller, we know that AP increase damping, respond faster, KI make response more oscillatory. However, PI can reject disturbance. PID can also reject disturbance. Yeah, you see just now that PI can reject disturbance and make steady state error to be zero, right? Yeah, so now what's the role of derivative controller in there? So we will discuss this on Wednesday. Okay, team who can answer correctly will get bonus point. Yeah, okay, I'll see you again. Yeah,
Ada homework.
that's a homework, right?
Homework.
A team homework
Method submitted.
not submitted. Yeah,
What's the role of KD?
yeah, what's the role of KD?
Then
So I will upload this to Canvas for you to check. See you again on Wednesday.